You're listening to 9 Plus, a research podcast from SETU Ireland. Greetings and salutations. Welcome to the podcast in which we explore interesting topics that people in the South East Technological University of Ireland have expertise in. My name is Rob O'Connor. For this episode, I sat down with PJ Cregg, a lecturer in electronic engineering, to capture some of the materials from a recent talk he gave on physics and photography. And this is where PJ explored a lot of physical phenomena, such as light, and described it via photography. This particular talk was delivered at the long-running Mathematics and Physics seminar series at SETU and is the third part of a trilogy of presentations by PJ on the intersection of science and art. We got into some of that in the podcast too, such as the relationship between mathematics and music, and Claude Shannon's information theory and James Joyce's Finnegans Wake. There's a few links in the show notes that you might want to follow up with. And now let's meet PJ Cregg, and you can listen to two grown men talk about rainbows.
Hi, so my name is PJ Cregg and I'm a lecturer in electronic engineering in the engineering technology department.
So PJ, we're going to talk today about a recent presentation you made on physics and photography as part of the Mathematics and Physics seminar series. If I was somebody who listens to this podcast, will listening to it help me take better photographs?
Well, I don't know necessarily about that, because I'm not going to be talking about composition or what makes for nice photographs. Really, I like taking photographs, but when I'm taking photographs, I often see optical phenomena that I think are interesting. And because I lecture in electronic engineering, and because the light is part of that, part of the electromagnetic spectrum, I see these things, and I've been, over the years, I've been taking photographs saying that would be nice to illustrate this feature. So I've collected photographs that illustrate those. So my goal isn't about composition or those technical aspects. It's really about a combination of understanding light better. And sometimes, you could use some of these features to improve your photographs. You could, but that's not where I'm coming from, I suppose.
Okay, well, let me ask you a fairly fundamental question to begin with. What is light? That's
okay. So
that's a big one. I know.
This is a question that has interested and fascinated scientists and people in general for centuries. I suppose where I come from this, I'd say to me, light is an electromagnetic wave. Okay, so we'd have to give a bit of thought to what that means. But there's that essentially is a 19th century vision of what light is. Subsequently, in the early part of the 20th century, we realised that light is more than a wave. It could also be viewed as particles, as these particles of light called photons. So in order to have a full physical description, from a technical level, you must take these two things into account. From the point of view of a photographer, though, light can be seen as a wave. Or there's even a simpler way of thinking about just thinking as rays of light. And we all have a sense of the idea of a ray of light travelling in typically in a straight line. So those would be my ways of looking at light.
Okay, and then let me ask you another fairly fundamental question, but this will hopefully frame the rest of what the conversation is going to go like. What is optics? Or should I say, what are optics in the context of this? I don't know if optics is a plural or a singular term. Yeah,
so I remember I work in electronic engineering, so optics isn't actually my area, so I can attempt a definition to say it is the study of light as it be light of a certain wavelength, the wavelengths we can see, but it also includes, as far as I know, infrared and ultraviolet. So it's a part of the spectrum that really, if you've got prisms or if you're putting light through glass and things like that, optical fibres, they're all in optics. So even say optical fibres, you can have ones that work in non-visible wavelengths. In fact, most of our telecommunication wavelengths aren't visible, but that's considered light, and that's part of optics. So that's how I would frame it.
It's funny because if you ask me, I suppose from a computer science perspective, if you talk to me about optics, I immediately think of lasers and optical media as such, if you know what I mean, like CDs or DVDs or anything like that. which just shows you that the same word can have different meanings depending on who you're speaking to. And I know they're all variations on the theme, obviously, because lasers are light. But,
and indeed on the CD, what you're doing, you're putting the laser down, and all those little etches on the CD, they're of the wavelength of light, and that's how it works for them. If we were to do the same thing at radio wavelengths, the CD would be the size of Ireland, roughly. Okay, I'd have to check the numbers on that, but it's ballpark.
Okay, well, I won't hold you to that.
Okay.
Right, so light, optics, physical phenomena that can be observed in photographs. So I didn't get to attend your talk, unfortunately, because I had to pick up children, which is kind of often my primary role. But there was a word there that in your slides, which you very graciously shared with me, and crepuscular rays.
Yeah.
And now, so I'm going to spell this because I'm making a bags of it. Okay. So crepuscular rays. What the hell are they?
Okay, well, I mean, we've all probably seen them, and I've been taking photographs of them, and until recently I actually didn't know the technical name for them. But of course I had to do some reading up to make sure that I'm conforming with standard language.
Did I pronounce it correctly?
Crepuscular, yeah, I think that's how you pronounce it. I think that's how you pronounce it, yeah. So what these are is you often see them, and they're sometimes referred to as God's rays. If you can imagine, a figure with an old man appearing in the sky and talking down to Moses. So these rays that seem to emanate from a part of the sky. Typically, you've got a cloudy part of the sky, and you've got these beams of light that are shining out. So typically around sunset you see them, and they're very dramatic, and they make great photographs. And one of the surprising things about them, you look at them and you see the beams appearing to spread out. But the beam lines are actually all parallel. And it's our perspective that sees them as spreading out. So in the same way as if you were to look down a train track, the two lines, we know they're parallel, but as we look at them, they appear to be moving towards each other.
Okay.
So it's perspective. It's our inability to really get the context of these to see that they are actually parallel lines. In the same way, there was a photograph I had of buildings, and we all know that a road has parallel parts, and you look at it and you know what it is. So your brain adjusts and tells you that. But when you're looking at these rays, we've no context to know that they're parallel. But you see them photographed from space or from an airplane, which I didn't get to do from an airplane, or certainly not from space. You will actually see that they are clearly parallel. Okay,
so what you're describing there is like, so you say God's rays, so it's like when you look out at the sky and you see like these rays coming through typically through the clouds, and it is very dramatic.
That's right, and they definitely look like
they look like they're coming out in all directions.
They look like the cloud is almost like the light source. That's what it looks like, but that's a perspective illusion.
Okay, so and that's what gives us a sense of distance. Is it or how does this work?
Well, I mean, it works because we're kind of in the middle of the field of the thing. The lines are if the lines were to run past you above your head, you'd see them as parallel. But because we're a distance from them. It's the same way. It's the train track is the best way to think about it. Okay,
so but is that to do with our perceptions and the way that is it to do with our depth perception of our actual vision, or is it?
It's a real thing. If you were to project, if you were to take it with a pinhole camera and project it on a screen, it's real.
Okay,
and it has to do with perspective, which is something, say that Leonardo da Vinci and these medieval or Renaissance painters would have looked at. They would have projected. The belief is they would have projected images through pinhole cameras to try to capture that, and it made for a much more realistic painting when you follow that. Whereas previously painters who would have tried to capture perspective would have failed, and you can almost tell. There's a point. I'm not an art historian, but I think there's a point you can tell an art when that shift is made, where they get perspective right.
Yeah, so it's funny that you bring up art, because as you were describing it, I was immediately thinking of kind of religious paintings, where God is on a cloud, extending a hand or whatever it might be. Yeah, okay. But what you're talking, so this is obviously a natural physical phenomenon.
It's real in the sense that a camera lens will capture as much as the eye. That's the way to put it. There are certain things we might think are just our own brain perception, but this is, if glass captures it, we have to kind of take it. It's real. Yeah.
Okay. You talked a lot about projections and the sun.
Yeah.
And a lot about how, it looks a lot of stuff about how shadows appear and different types of shadows. So could you maybe explain some of that? as to maybe what some of the interesting aspects of shadows are.
Okay, so just like I was saying with the crepuscular rays, that's a nice example where we can use the ray model of light. That's that light travels in a straight line. That's how we view it.
Yeah.
Now, if we think about the sun, though, if we think about the sun, it's actually a disk. It appears to us as a disk in the sky. So if you think about, say, the top part of the sun and the lower part, they're essentially two light sources. So the top part is going to come in one direction, and the lower part is going to come in another direction to a narrow gap, shall we say, right? To a narrow gap, like a hole in the leaves. And with the result that you actually get the image of the sun will actually appear inverted on the ground. Now, there was an extreme example of this. I was staying with some friends over in London, and it was a very sunny day. There was a tiny gap in the corner of the curtain, and projected on the wall, you could see the clouds upside down travelling along. So it's the same thing you get in this. I spoke of the pinhole camera that the Renaissance painters used. So you get a full projection on the wall. And if you think about it, see each point out in this plane, in one here, has travelling through a single point, which is the pinhole point, has a corresponding point at the other side. So our sun, if we see the sun here, it'll appear as a little solar image. So the sun will appear as a little disc on the ground. So say if you're, there was a photograph in the presentation. It was actually, I was having dinner outdoors in the summertime, and there were trees maybe about 8 meters high or that kind of height. And on my table were little circles around 8 centimeters. Well, basically for every 1 meter, you'd expect 1 centimeter, roughly the size of the circle. So there were a number of little circles dancing on my plate as the leaves rippled. And actually, I think I mentioned, or in the presentation, I mentioned that James Joyce discussed these. He called them dancing coins. So at the end of one of the sections, Ulysses, Stephen Dedalus talks about it. It ends with these dancing coins. So they're a very nice thing to look at. It's one way if we ever got the opportunity to see a solar eclipse again in Ireland, well, the next one, some of the people listening out there may get to hear it, because when is it again? It's in 2090. It's going to be the next total solar eclipse in Ireland. So there will be people listening, please God, who will be still alive when that happens. And you can look at it to your shaded glasses to look at it, but you can also look at these projections would actually show you the solar eclipse. So on those little circles, you'd see the moon start to eat into it, and you'd get a projection of the eclipse through the leaves.
Right. God.
So they're everywhere to see. So if you're it's the dappled light you see in a wood. If you're walking through woods, you look in the ground, you will see them. So one of the things I would like to do is that when people are out enjoying nature, enjoying the beautiful scenery around them, notice these little things as extra features of to delight in or to enjoy.
Yeah. So it's not really necessarily to do with photography. It's just to do with the photography is okay. You're applying it through the lens of photography. If you please excuse the pun, right?
Indeed.
Okay, but these are just phenomena that we see in our everyday life, but we probably don't often. We see them, but we may not observe them.
That's right, and we can miss them. We can miss them if we don't know about them. For instance, because as I'll say later, I found a really nice book on this, and what was nice, the book confirmed a lot of things I've been seeing and confirmed the explanations, and had nice diagrams to illustrate it. And the book was written in 1954 by a physicist, but it also suggested things that I could look at that hadn't occurred to me. So I started to see more than I would have previously seen. And I suppose there's just some nice things out there that people can keep their eye out for. And it's nice to appreciate, but also to understand. There's a certain pleasure in understanding what you're seeing.
What is the difference between reflection and refraction? Okay,
so we think about a simple thing like a mirror. Light bounces in a mirror and all of it bounces back again. That's clearly... So the idea of reflection is clear to most of us, right? So in that case, on a metal mirror, all the light bounces back again. And we could do some geometric things. We could see that the angle that the light comes in is the same as the angle it bounces out. In a way, if you threw a ball on the ground, same way as you threw a ball on the ground, it would bounce out. If there was no energy being lost, it would bounce out at the same angle. Whereas refraction occurs in, say, water or in glass. It occurs whenever we change media. Say if we go from air to glass or air to water, the different media, some of the light will go through and some will bounce back. But the stuff that does go through, interestingly, it changes direction. And this change in direction can actually be explained, or rather we can help understand it by using a principle called Fermat's principle of least time. And this, to me, is one of the most beautiful principles in physics. And it applies to light. There's a corresponding principle in mechanics called the principle of least action. that we could talk about perhaps on another occasion. But today I'll stick to the principle of least time. And what it tells us that the second piece we need to bring to the table is that when light travels through glass or through water, it slows down. So we all know about the speed of light, and we know it's a fixed constant for nature, but that's the speed of light in a vacuum, you see.
Yeah, it's 300,000 kilometres per second or something like that, isn't it?
I think you have it, yeah. It's 3 by 10 to the 8 metres per second, so that's 300 million metres, so 300,000 kilometres,
okay.
Yeah. Yeah.
Okay, fair enough. There you go.
Well done, Rob. So
thank you.
Yeah. But when it goes into a medium, say if it's glass, it slows down to 2/3 of that speed.
Oh, okay.
And if it goes into water, it's down to 3/4 of that speed, right? So this is where Fermat's principle of least time is. Light chooses, well, if we think of it as a sentient being, light chooses the path of least time, right? So think about it. The example I use, say there's somebody drowning in the water and you want to try and save them, right? Now, you have different choices how you get to them as quickly as possible. You could just go in a straight line. But then you're going to spend quite a long time swimming, right? Because, and swimming is slower than running. You could go so that would be the path of least distance, right? You could go for the path of least swimming. So you run to the shore until you're perpendicular and you run in there, you swim from there. But that isn't necessarily going to be the optimum from the point of view of time. So the optimum from time takes into account the fact that we can run at a certain speed and we can swim at a certain speed, and they have a ratio to each other.
Right.
So if you want to get there in the least time, you want to cut down your swimming, but you don't want to maximize your swimming. You want to just get the right balance between running and swimming. So that is the route you go. So you run a bit and then you come in at an angle. And the best way I can put it to you is if you throw a stick into the sea and the dog goes into it, a dog knows how to run like this. It doesn't go in a straight line because it doesn't want to get into the water too soon. So it comes at an angle and then it goes in. And that is what light does. It goes by the path that takes the least time to get there. So I said that, say, to glass or water, you go slower. So you don't want to be going through glass or water too much. So this is a way of showing us the angles, what way the angles go when light goes from air to glass.
Okay, you've kind of lost me.
Okay.
That's just no. But that's nothing to do with you. That's to do with me. That's because I'm not a physicist. I'm not an engineer. But I'm interested. Okay. So I'm gonna hit you with another question then about on the same subject that might make things a little bit clearer for me. So what you're talking about there is that light likes to take the path of least time. Which is how it gets from point A to point B quickest.
Yeah.
Through whatever medium that is. Is it also going through in the straight line, but because it is slowed down considerably, we observe the quicker path beforehand?
Well,
do you get what I mean there by that?
I think I do, but and perhaps there might be a way of seeing it that would say it's going in a straight line. Certainly, if you apply this to gravitational fields, you could say because this happens when light goes around a massive thing like the sun. Light bends around the sun as well, because what happens is that gravity changes at time.
Yeah, am I right about that? Sorry, I know we're going off topic.
Yeah.
Because this could be a stupid question, and if it is, please humour me. Okay?
Yeah.
Gravity affects physical objects. If light is a wave, but it's also a particle, will gravity affect light? Okay, you're saying
it will indeed. It will indeed. Yeah, and because light has to travel through space-time, and space-time gets warped by gravity. So you can look at it through, because it is like a particle. Look at that, but it basically another way of looking at it, space-time is warped. So it's warped for everything. It's warped for light as well. But you see, what I like is we can apply the principle of least time to this, because what happens when you're near a massive object? Now we are getting a bit off light and getting off topic in some ways because we're getting off photographs, but let's stick with it, right? Because it applies. The point is, this principle applies wherever we encounter light, and even all electromagnetic radiation. So it's a beautiful principle to apply. So around a very massive object, time is actually being slowed down.
Okay.
So if you were to travel in the direct line of sight, you'd be going through a region of space where time is getting slowed down. So you'd be getting held up, basically. So what light does is it avoids that and it goes around it. So you get what's called gravitational lensing. So around a massive object, if it's a very, really dense thing like you'd see out in deep space, you can see what's called Einstein's rings. You see a star, that the light from the star is going the whole way around another star in order to avoid getting into its high gravitational field. So we see a ring.
Okay.
Yeah, so it happens in space, but it can be used as a principle to help us understand just what we would call simple enough ideas as to how light bends when it goes into glass, you see.
Okay, now let's bring this back to photographs and visual phenomena that we can see or photograph.
Yeah.
And taking what I have just learned about reflection and refraction, and it started off with that question. Is this where the likes of a rainbow would come from?
It is. It is the likes of where a rainbow would come from.
Because that's going to it's going to rain, water. Yes. Yeah.
Okay. So, I mean, the rainbow is a fascinating thing. Let's face it. I mean, and we have the phrase "the colours of the rainbow" coming from it, right? And you know the perfection of it and its circularity. It's fascinating, right? If we understand how it's happening, basically, it's caused by raindrops. The light's coming into a raindrop. Now, when light comes into a raindrop, it goes from air to water.
Yeah.
So it actually gets its direction gets changed slightly. So it goes into the raindrop and has to turn. Now, when it hits the other side of the raindrop with a view to leaving it, not all of it gets out. Some of it reflects off the surface, the internal surface of the raindrop.
Yeah.
And it bounces. And then it has to try to get out again at the other side. A large part of it leaves at that stage. And that's what we call the primary rainbow. Now, added to that, glass and water, they will give you the rainbow. We all kind of know from various sources, whether it's the Pink Floyd album cover or whatever, we see light coming in and we see it splitting up, right?
Yes.
So we know that these things can give us the colour of the rainbow. So we were going to get that through the refraction, right? Because different, not to get into too much detail, but different wavelengths travel at different speeds, you see. Okay. So that's why they change their angle when they're coming in. They travel to different angles because some colours go faster than other colours.
Really?
Yeah.
I did not know that.
Well,
every day is a school day. I thought that light just travelled, that red light, blue light, the same.
In a medium, they change. They have different speeds.
Oh.
In a vacuum, they all travel.
Okay.
The same. That's in the medium, and that's what gives us these different angles. You see, because the ratio of the speeds is what takes what path you'll take.
Okay.
And so red and blue will take different paths.
And then, right, so just go back to the rainbow. And I feel like I'm getting a personal tutorial here, so thank you. It's not just hitting one raindrop; it's hitting thousands or millions.
That's
right. So it's being refracted, and reflected,
and then refracted,
and then going
again.
On to the next one, and the next one,
then leaving the raindrop and coming towards you. And there's the angle that occurs we can predict that angle basically. So there's a simple enough geometry. When the sun has to be behind you, right? And if you think about the line that between yourself and the sun behind you, take that as a reference line. If you go 42 degrees off that line, that's where your rainbow will appear, and that's why it's in that arc along there. But
because it's always 42. Okay, right. So are you telling me the 42 actually
means something? It is. It's the answer to the rainbow and all else.
The rainbow. Okay, so that for any nerds who are listening,
it's not the only
answer.
It's not the only answer. But why? Because there's a second rainbow as well. Remember, I said that the light comes in, it refracts, bounces off the surface, and then it comes out the next time. A lot of it leaves. Some of it does another loop. And what you basically see is this thing called the secondary rainbow.
Yes.
And that's at 50, I think that's 51 degrees from your... But the interesting thing about the second rainbow is inverted in colour. So there's the thing to definitely watch out for. So when you look at your first rainbow, it goes from your side, it goes from... I think where we're looking at it, which colours... if we had one in front of us, we'd know. But I think it goes... I won't guess. It goes... The colours that go one way, they flip the other side. I think it goes from red to blue and then goes blue to red on the other side.
Okay.
But if you check one, you'll see. Another interesting feature is...
But can I just ask you, because often it's only on a particular day that you can see the two rainbows.
Yes.
Do you know what I mean? Now, it is quite a stunning sight. I actually saw it recently enough this year over the bay in Dunmorris, actually. Where
it might have been the same picture I got. Okay. I had in the presentation. It was... About a month ago.
It could have been.
5-6 weeks ago, yeah.
Yeah, it could have been. I was collecting the kids from school.
Yeah.
And it was one of those...
I caught it in the garden,
Yeah, it was one of those stop you in your tracks moments.
I tell you, wow. I'll show you the photograph and there's some beautiful lines in it, Okay,
but so how is it that on some days you can see it and other days you can't? Is it to do with? Is it just something as simple as cloud cover? Is it?
I think it's I'm telling you, it's the strength of the sunlight. Basically, would be the thing I see as most important. If the sunlight is very strong, it's exactly cloud cover. Because what you need sun and rain. Now in Ireland, we're lucky we get these two things a lot, right? So if the sun is very strong, then the reflections are going to be stronger, you see. Because think about it, the light goes through the raindrop. Now, not all the light's reflected. So only a small part's reflected. So every bounce, every reflection, you're going to lose energy. You're going to lose light level. But what's interesting is it can easily be missed as well. You got your two bands in your double rainbow, but there's a dark band in between. That's worth looking out for, called Alexander's Dark Band. It's named, and
be a great name for a real band.
Yeah, yeah, for sure. And the way I look at that is, well, we're getting the extra light from the rainbows. Somebody has to pay for it. So the dark band pays for it. That's the light that's missing, in a sense.
Okay.
You see, because the light's not going to the raindrops, it's coming back to you. So it's not going onwards.
God. This is fascinating stuff, PJ. I mean, I wasn't intending on getting down this road, but I find this kind of stuff interesting in a novice kind of a way. Because, I mean, I suppose, like most people around SETU or in academia in general, I think we're all kind of curious. Mightn't all be curious about the same things, but we all have curious minds about a whole variety of different subjects. And I kind of want to jump off talking about physical light, or talking about light and photography for a moment, and kind of pull it back to where you delivered this talk and the context in which this talk was delivered. So this was part of the Mathematics and Physics Seminar Series, which for as long as I've been haunting this place, so I've been working here now since 2006, I think it is. There's been this seminar series has been running, and it's been going longer than that.
That's right. Well, I'm here since '92, and it was running then, and it goes back before that. So it's, as far as I know, it's the longest running continuous seminar series within the college. Okay.
And is the idea that it's open to anyone to? It says maths and physics, but here you're talking about photography. If what I mean is that it's not just a load of people sitting around drawing equations up on the board. You're nodding.
Yeah, but I mean, I'm able to shoehorn it in because it's physics and photography. I suppose that's it. That's the way that it fits in.
Okay, but I'm looking at you deliver this as the third part of a trilogy of talks, none of which I have attended, and I'm kind of kicking myself because I think I'd love this. So the first one you did was called James Joyce and Information Theory. Is that it?
It was Shannon's Information Theory and
James Joyce's Finnegans Wake.
Yeah.
Okay, I haven't read Finnegans Wake, but it's on my list.
Yeah.
It's on I read Ulysses over COVID.
Did you spot the dancing coins? You might on a replay.
I might have to read it again, and that'll be the next. If there's another pandemic, I'll probably read it again. The second one was Mathematics and Music.
Yeah.
Which again, I don't know what the formal stuff there is, but certainly I can appreciate the patterns and I can see so many links between music and mathematics. And then Physics and Photography. So what I think is kind of interesting is as you're delivering these talks as part of the seminar series, you're kind of clearly pulling on things that appeal to you as a person, because I know you're into music and I know that you're into photographs, and I'm going to assume based on Joyce that you're into reading as well. Okay. So I think if we're talking about looking at light through the prism of photography, okay, what I think is interesting here is that you're kind of talking about science, and I'm using inverted commas because this is a very broad term, okay, but you're viewing it through the prism of art, and you're nodding.
Yeah.
Why do you think that is? Okay,
well, I suppose, I mean, what can I say here is the three talks are professionally based on I do communication engineering. There's a lot of maths and physics in what I do. So those are the technical things that interest me. But as you say, I like literature, music and photography and art and things like that. So I was lucky enough to be able to combine these. I suppose I see patterns and things. I see similarities between things. And they interest me a lot. And the idea that these two things of arts and science can't communicate or don't help each other, I think is fallacious. I think it isn't actually the way it works in reality. I think, say, Turner as a painter, I'm sure he knew the chemistry of his paints. Yeah. You don't produce those beautiful watercolours just by dabbling with paint, you know. He knew his... So the really great people like Johann Sebastian Bach, they have in music, they have a deep understanding of patterns and what makes music. They're great technicians, is my point. In order to be a truly great artist, these people are great technicians as well. So that's definitely an area where you get to the highest point of these disciplines. There, you can see an overlap. And Joyce in literature, he actually described himself in, it's quoted in Ellman's biography, he said, He described himself as an engineer. That's what he actually described himself as.
Really?
As a language engineer, a linguistic engineer. I'm wrong. Communication engineer was the term he chose. And in Shannon's information theory, he only quotes. So Shannon was this man who basically gave us the digital theory, the communication theory that is the backbone, we could say, of the digital age. I mean, Viterbi, one of the key players in mobile comms, said that without Shannon, if I'm quoting correctly, without Shannon, we'd have what we have now, but we'd be 20 years behind. So the theoretical backbone that Shannon gave us was a huge help to understanding what information was. Because at the time we had telecommunications companies with telephone lines, but nobody knew what were they really selling. What is this thing? Now, of course, we know we're in the digital world and we talk about bit rates and what we know about, we can quantify it. But that was Shannon who quantified it by naming bits and quantifying information levels. So,
really?
Yeah. But
I'm learning loads of this.
But the fascinating thing is, and I noticed this in my first year here in 1992, I noticed this in reading Shannon's book, The Mathematical Theory of Communication. It was a paper that later became a book. It's in the library. The only book he refers to is Finnegans Wake.
Why?
Why? Because the text of Finnegans Wake is the perfect playground, whatever, for him to examine information theory. Because one thing about information theory is, say if I send you letters, if I've sent you the phrase "the dog barks," the letter O is missing, the letter A is missing, you'll still be able to figure it out because of the context. Because there's very little information in the second O. Because you know it's not going to be dig or dag or dog or dag or whatever. It's going to be most likely going to be dog. So that's called redundancy in written text. And so what Shannon was able to do is figure out how much information is really in a sentence or in a communication, whatever it is, whatever is being sent.
Okay.
And it's based on what redundancy is in there and how predictable things are. So you can look at the statistics of the English language and you can then quantify how much information is in a written text. Now, the thing about Finnegans Wake is, if that O is missing, it's another letter, it means something, because Joyce would have a word and he put in an extra letter or he put in a different letter, and there's a huge amount of meaning laden into that. Okay. And so that's how he was able to put more information in, but at the price of loss of redundancy. So these are classic ideas, shall we say, in information theory. And my belief is that Shannon chose this because, as I say, it was a great experimental text for him to try to do quantification of information on. And he gives a nice line on it. He says that, but he did say allegedly, he says that Joyce, by removing redundancy, he allegedly introduced more information content. Because Shannon was very much a practical scientist in terms of he didn't like going beyond what could be said about his theory. He liked it to be applied for what it was applied, what was intended for. He didn't like a kind of a flowery version of it, shall we say. So he wouldn't say included more information because he didn't know, because he would claim he would, that would be, so he said allegedly included more information. Okay. Yeah. Okay. That's a typical kind of scientist answer. Yeah, exactly. Don't say more than you don't about which you don't know, don't speak. Yeah. Well, which maybe we should all do that. Yeah. That's another day's work. Yeah. Okay. So just to go back to the maths and physics seminar series. Yes, indeed. And there's one on today, the day we're recording, which can't go to either because I have to collect my children. So there you go. What can I do? Again, primary role. That's where I must go. Let's say somebody was listening and said, "Do you know what? I'd love to go along to one of these. What's the story? How do I learn more about it?" Well, you can get on the mailing list. Brendan McCann is currently organising them. Mm-hmm. So if you contact anybody in the School of Science, or indeed anybody in the School of Engineering, they could send you in the right direction. But Brendan is in the School of Science. He'll put you on a mailing list and you'll hear about when they're coming up. So they're intermittent. They're not on every week. They're myself and Gabriel are giving ones this semester. I hope actually to repeat the physics and photography next semester. Do you? Yeah. Great. So there'll be an opportunity to see and hear that one again for anybody who wants to come along. Will you do the maths and music one again? Purely for me. I will, Rob. To go. It's one actually I've done it twice now. I did it twice last year, so I'm more than I do these all day long if people are interested. Well, I remember going to one. Now this is I could have my dates wrong. I think I went to one of these a number of years ago, and there was a man who used to work here by the name of Michael McGettrick, I think, and he did one on the maths of music, and it was all about rhythms. He was talking about beats and rhythms and why we, and I say we as in humans, why we like some beats over other beats.
and it's to do with order and repetition and things like that. And I don't know the full details, but it's like everything about art. I don't know much about it, but I know what I like.
Yeah.
Do you know what I mean? And why is it that when there's a groove that we get into it? And I thought it was fascinating. So anything that I can learn a bit more about the kind of the science or the theory that's underpinning various aspects of our lives is surely to be applauded.
Well, if I was to do that, it would be complementary to that, because I don't mention rhythm at all in mine. It's actually about the different frequencies that are used. The frequencies sound pleasant to the ear, and there's certain ratios that sound good, and other ones that don't. But it's similar. I mean, it is similar idea in terms of pleasantness and not pleasant, and you can account for them and explain them by looking at ratios.
Yeah. So this is like where you have like, I don't want to get into octaves and semitones, but
that's where you're coming from, exactly, and the fifths and various intervals, we'd call them. Yeah.
Cool. So look, if somebody is interested and wanted to head along to any of the Maths and Physics Seminar Series talks, drop Brendan McCann an email, brendan.mccann@setu.ie. I think is going to be his address, but if not, I'm sure you can contact yourself, which is...
So that's, let me see, what is mine in the SETU world? It's PJ Cregg.
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 At setu.ie. And what I'll do as well is I'll put a link to staff profiles on the show notes. Great. For this podcast as well. Before I leave you go, PJ, I have one last question for you, which is kind of off topic, but is also very much on topic. Let's say somebody was listening to this and was a novice researcher or not a researcher and was thinking about getting into a bit of research. Have you any bit of advice for them?
Yeah, well, I suppose I'm thinking about it. I would perhaps view research into different categories. The stuff I'm doing here and talking about here isn't really research, but it's me exploring ideas that I think will help in my teaching and trying to connect various things. And if I found various interesting things, it's because I've kind of followed. If I find something interesting, I kind of chase it. And I try to find out more about it. And perhaps I've been looking at some of the things I've found in that. So that's one aspect of what I would do. But in terms of the research I do that gets published, obviously some of those characteristics are going to be present there. In other words, follow your nose. If you think some idea might work, don't be afraid to try it. To be successful at research, there's a lot could be said about it. It's not an easy thing to give you a recipe for. I mean, I suppose I've been lucky. I followed an approach. I followed my nose on things and tried to follow a route that appeals to me. So, I don't know what advice I could give that would work in a general sense for people. It really depends on the individual and what their strengths are and their interests are. But if I have been successful, I mean, for instance, I gave a talk on the tides, and that stemmed from the fact that I'd overheard people saying that, the tides were particularly strong because all the planets were aligned. Now, I heard this and I thought, well, I'm a kind of scientist, engineer, and mathsy guy. I should know whether this is true or not, but I don't recall ever being taught it. I had no idea my feeling was it wasn't, but I had no way of refuting it. So I started thinking about it, and I started thinking about, well, what causes the tides? And then I got a model of it, and I wrote down a few equations. I got a few simple ideas. And then I said, okay, well, if what I'm saying is true, the sun should be less dense than the moon, for instance. And I follow it up, and it turns out it is true. So then I know I'm onto something. So what I'm doing there is just following something. It's a bit like a grain of sand getting into an oyster. It bothers you, and it annoys you. And until you can wrap it in a pearl and throw it out, you won't be happy. So that led to a paper in physics education and a talk I gave here and a talk I gave to the Institute of Physics. They had a kind of an annual meeting in the college. And I have to say, I mean, I'm lucky that was well received. Yeah. And that only stemmed from the fact that this thing annoyed me and I wanted to seal it and wanted to get rid of it. I wanted basically to satisfy myself, but also say, wouldn't it be nice if there was a paper out there that filled in this gap, so if somebody wanted to know, they could read it, or a physics teacher could present it to their students so that when they go out into the world, they would know the answer to that question and they would see that quite simple mathematics can show things and refute claims that are baseless to some extent. Now, I mean, the tides are affected by the planets, but a hair's breadth. Mm. So in principle, it's right. You see, when you actually put the numbers on it, it doesn't count. So that was an idea that I followed up until its conclusion.
Follow your nose. I think that's good advice.
Yes.
That's very clever. I think that's very sound, not just for research, but also for lots of other things. Particularly any dinners that you might eat.
Fresh food, yeah, you'd smell before eating.
Exactly. To PJ Cregg, if you want to find out more, I will have some links in the show notes. Thank you very much for speaking with me today. It's been an absolute pleasure, and hopefully we might follow this up again at some stage in the not too distant future. Indeed, Rob, and thank you very much for the opportunity. I enjoyed it enormously as well from this side. No, but flattery will get you everywhere. Thanks for listening to this episode of 9+. For more information on this podcast and others, check out the new SETU website at setu.ie.